Okay, hello everyone. My name is Margherita Miccio, and in this presentation I will talk about an utility I have been developed in OpenFOAM 13 to do the reaction path analysis, and I will use also graphics to visualize them in a diagram. So before starting, I wanted just to give some context, very basic. As we know, we live in a world where every event can be described by a reaction. So, for example, the bread leavening, the cellular respiration, the combustion, all of them can be described by one singular reaction. But what is happening instead is that every single reaction has a lot of intermediate reactions that are happening, and that is important to analyze in some situation, such as in the combustion. What I work on is combustion processes. In this case, we will analyze the methane combustion through some reaction pathway diagrams. And it can be important to analyze this diagram because we can understand in this way how exactly the pollutant, the final species, are produced. So in order to understand this, let's see this reaction. So the methane is the fuel, and then it will meet the oxygen to form the two products, so the CO2 and the water, plus some heat, of course. This is one single reaction, but can be also represented in a more complex way. So with this type of diagrams that we see here, where we can observe that a lot of intermediate species are also produced in the process, not just CO2 and water, but also a lot of other species. Through other smaller and faster reaction, which involve, for example, radicals such O and OH. So let's try to understand how exactly we lead from the first reactants to the final product. To understand this, we can have a look again at this sketch, and we need to understand that, so in our system, we will have a lot of species competing and meeting with each other. So in this case, we will consider a cubic domain like this one. And so in a computational domain, we will have a multi-component fluid characterized by a lot of species, such as the one in the slides. This system is a system that needs to be solved. And since we have not anymore a single component fluid, we need to solve every single mass fraction that is involved in the reactions. And then we need more equations that involve also the species transport equation. So we will need to solve first the continuity equation, as usual, and then we need to solve the species transport equations, which are M equations. So because we suppose we have a system with M species, so we have M species transport equations in order to solve each of them. Then we have the continuity equation, the momentum equation, and the energy equation. So by solving all these equations, at this point, we know all the variables that are to be solved in the domain. So we have the density, we retrieve the pressure, the temperature, the mass fraction, and the velocity. But the mass fractions, so is the gives the information of how much of each species we have in the domain. But we don't want just to know how much of them we have in it. We also want to know how they are formed. So we need to know how they are formed, which law govern their formation. And so, for example, to understand how the pollutant in the combustion is formed in order to maybe manage to limit this production. And then we need, so once we understand the law, we need to also gather the data about it. So in order to understand how they are formed, we can have a look at the image in the slide, and we will see that we have the methane meeting with the oxygen. They will meet and then they will react together to give an intermediate species such as the CH3 and the water H2O. Then we will still meet a new radical, the OH, with the CH3. It will once again react to form CH3OH to form CH3OH. So this is how they react. They first need to meet, then they will react to form some intermediate species. And then we need at this point to understand how we can visualize this in a reaction path diagram. So this can be observed in here, once again, by considering these two reactions. Here we see that we have the CH3O in the red circle, which is forming a new product, the CH2O, by meeting the OH. Once it meets the OH, CH3O will lose an hydrogen, as is shown by this part by the label of the arrow. It will lose an H to form the CH2O. And once again, this CH2O will interact with the OH to form a new other intermediate species, which is the HCO. Now, we need also to understand at this point for every reaction how each element is moving from a reactant to a product. If we start tracking the carbon atoms, we can see that in this case we know exactly that the carbon in the CH2O is coming from the CH3O because there are not other possibilities. But if we consider the hydrogen or the oxygen, there could be more interpretation because, for example, for the water, we cannot a priori know if the H from the water, the hydrogen, is coming from only the CH3O or also from the OH. So we cannot univocally identify where each element is coming from which part is coming each element. And so we need to solve this ambiguity numerically. How can we do it? First, we may use some heuristic rules for the element flux, so to calculate this flow of elements from the reactant to the product. So one rule is to prefer single exchanges over double exchanges. Regarding the double exchanges, I can explain this situation by considering that each species in the reaction can be divided into molecular fragment. So every letter inside this reaction will be a molecular fragment, and we can see that here in this reaction, here we have two molecular fragments that are exchanging during the reaction. Instead, the single exchange is where only one molecular fragment is moving from the reactant to the product. In this case, is the small a is moving from the reactant, the first reactant to the second product. An example is the same equation we used previously, where we can see that we can now understand where the hydrogen in the water is coming from. It is coming from the CH3O because this case just wants to use the single exchange. So using this rule, we can now really track where the hydrogen is coming from, while before we had some ambiguity. We didn't know which interpretation to choose. The second heuristic rule is that we should minimize the atom rearrangement. So if we have some single exchanges possibilities, or if we have more possibilities of single exchanges, we need always to prefer those involving the fewest atoms, and among these always prefer minimal atomic weight transfer. And the third one is to try to preserve the carbon-oxygen bonds because those ones are the strongest usually. Now, let's understand how this is implemented in the post-process utility I developed. So first of all, we need to have solved the Navier-Stokes equation, and we need to have already the information regarding the species concentration in the domain. After this, we can start with the post-process and use the utility that is called element flux that will track the flux of a user-defined element A, which, for example, can be carbon. So at this point, once we run this utility, we can visualize then the diagrams like the one I showed before, and see the reaction pathways. At this point, let's consider this equation. This is one of the equations included in the reaction mechanism of the simulation. And we decide, let's track the atom of hydrogen in this case. We call the first reactant species J and the first product species K. And we can already calculate the element flux using this formula, where the NaJ is the number of atoms of hydrogen in the species Z, NaK is the number of atoms in species K, and then NaI is the total number of atoms of hydrogens involved in the reaction. So in this case, it will be 10 because H3 plus H7 is 10 atoms of hydrogen. So just to make an example, we have here the species J and the species K. In the species J, we have 3 atoms of hydrogen. In the species K, we have 8 atoms of hydrogen. So we multiply 3 by 8 by the reaction rate, which is the velocity at which the reaction is happening. And we divide everything by the total number of hydrogen in the reaction, which is 10. So let's see how this is calculated directly in the code. We need to implement this equation. And so we enter in a if cycle where this is calculated. We say that we want to calculate this quantity only for the reactions that have a total number of atoms A. So for example, in our case, the hydrogen, which is greater than 0. Otherwise, we ignore this. We keep this value equal to 0 because it's not contributing that reaction. So we multiply the number of atoms of J, the species J, and the number of atoms of hydrogen always in the species K. We divided all of it by the total number of the atoms we want to track. And this will still be a scalar, but then we multiply it by the reaction rate field, which will be the reaction rate, the Ri in the formula, which will be a field because it will change among all the specific cells in the domain. It's not anymore a scalar. So at this point, we can calculate all these numbers, like especially the NaJ, the NaK, and NaI, with some helper function that were implemented at the beginning of the code. They will count the amount of atoms in one species and on one side of the reaction. So the first helper function is called the count atoms in species. And what it will do, it will just calculate the number of atoms in one single species by calling the n atoms member function of the class species element. So it will, in this way, give as output the counting that was done for every species. And then we will also implement another member function, another helper function, which is count atoms in reaction side, and it will count for each species the number of the atoms of that element, and then it will sum up with the other species included in the right-hand side or left-hand side. In this case, is from the reactant side, and it be multiplied by the stoichiometric ratio because we need to preserve the mass conservation. So to calculate the total number of atoms involved in the reaction, we need, of course, also to multiply by the stoichiometric coefficient. At this point, we observe in the code a new quantity, which is coefficient flux, which is multiplying the element flux we computed in this way previously. What is this coefficient flux? To understand what is the coefficient flux, let's have a look at this example. The example we saw previously. We calculated the Aijk in this way, but what is happening if we calculate in this way is that we consider that all the hydrogen in the species CH3 will all of them move to the species C4H8, while this is not what is really happening, because what is really happening is that only one of these hydrogen will go to this product, to the C4H8, and the other 7 hydrogens are coming from the second reactant. So if we implement the formula as it is so far, we would introduce an error, and we need something that corrects this element flux. That's why we need this coefficient that needs to correct the number of atoms that will flow from the species J to the species K. In order to calculate the value of this coefficient, we will use the heuristic rules we mentioned before. In particular, what I implemented in this utility was only the heuristic rule 1, which is prefer the single exchange. And this is done. In the next slides, I will explain how this is done. First of all, we say that the coefficient flux has to be set equal to 1 if there are 2 or 3 reactants and 1 product with the element we want to track. So if we have this situation, we will put this coefficient equal to 1 because we don't need to correct anything. We already know that all the atoms from the reactant will go to the only product that has that element. So we don't need any correction. The formula is correct already. The same if we have 1 reactant and 2 or 3 products with that element. No need reaction because there are no ambiguities. They will all come from the only reactant that has that element. But then the coefficient flux is unknown and needs to be calculated if we have 2 reactants and 2 products with the same element, with that element, or even more than 2, of course, but it will create even more ambiguities. So to do this, I will use the heuristic rule 1, which is the prefer single exchange. And to do this, we need to introduce a new concept, which is the group transfers definition. To define them, first we need to consider a reaction in this way. So we have 2 reactants and 2 products. B0 is a first group transfer, will be P0 minus R0, and B1 will be P1 minus R0. And to calculate this, let's have a look at this example. So B0 will be calculated by subtracting to the product 0 the number of atoms of the reactant 0. So in order to do this, we have in P0, for example, 1 atom of nitrogen, and also in R0 we have 1 of it. So 1 minus 1 will give 0. Then the same we do for the hydrogen. So we do 2 minus 3, and we have minus 1. And still in the example, we also add the 0 minus 0 for the oxygen. And we do the same for B1, the same subtraction from the product to the reactant, and we obtain minus 1, and 1. So this is how we can calculate the B0. But what does this B0 and B1 actually mean? They are group transfers, and a group transfer represents a hypothetical molecular fragment that, when combined with or removed from the first reactant, produces the corresponding product. So the molecular fragment B0 or B1 will be the one that, the big B, the capital B that we see in the last reaction. And this will represent a molecular fragment that will be combined with the first reactant, so with A, and when it will be combined with it, it will produce the corresponding product AB, as in the reaction. So it's a sort of molecular fragment that is moving from one side to the other in a simple way, so with just one transfer. And that's why we are here using this rule, because it allows to these group transfers, because it allows us to prefer the single exchange. So now we keep in mind this definition, and we see how this coefficient flux is actually calculated. Still again. The group transfer is considered valid if all the elemental coefficients have the same sign. Instead, it's not valid if all the elemental coefficients have different signs. So let's have a look always to the previous example. B0 was 0, minus 1, and 0. So it was valid because it's all non-positive. 0 doesn't count. And then we have B1 instead has minus 1 and 1. So it doesn't have the same sign. And B1 is not valid as a group transfer, while B0 it is. The second example that we will see will have both B0 valid, here is non-positive, and B1 also non-positive, but still valid. So in this case, the last case, we have two group transfers valid. So we don't know exactly which molecular fragment we need to select and to move in the reactant, because we have two possibilities. And so the reaction is still ambiguous and cannot be tracked in the element cannot be tracked in this way. Instead, the first example, we only have one possible group transfer, and it's what's happening here. The group transfer is just the hydrogen, in this case, which is moving from the first reactant to the second product. So we are moving the hydrogen from the NH3 to the water. And here, then the element tracking, so the element tracking of the H is successful. At this point, we can observe that this group transfer can be treated as a vector. So because they have the same number as components as the number of elements involved in the reaction, because we have several components. So in order to treat this from the code perspective, we will treat it exactly as a vector with the number of components equal to the element in the reactions. And we will count, again, with the helper function I showed before, we will count the atoms in that species by multiplying it also for the stoichiometric coefficient. So once we calculate the number of atoms in each species of the reaction, we can proceed then calculating the B0 and the B1 by subtracting from P0 and P1 the R0 vector. And here it comes the validity check, because as we said in the previous slide, we need to check if the group transfer is valid or not. So if B0 and B1 have all the same sign or not. So for example, let's consider only for now the vector B0. We need, first of all, to, as we see from the code, we need to calculate the minimum of the vector B0 and the maximum of the vector B0. If the minimum of this vector is greater than 0, it means that they greater or equal to 0. It means that B0 has whole non-negative components. Instead, if the maximum is lower than 0, it has all non-positive components. If this is true, then it means that we can find a B0 which is valid, and we will have a group transfer. And the same we do for B1. Now, if B0 or B1 are both valid, if B0 or B1 are valid, it means that we can choose only univocally one group transfer, and the solution then is known. Instead, if B0 and B1 are valid, both of them, we don't know exactly which interpretation we should take, so the reaction is ambiguous. And the same if both of them are not valid. So if we have different signs. In this case, in the last two cases here, the reaction will be ignored. So we will put coefficient flux equal to 0. So the element flux will be equal to 0, and that reaction will not be taken in account in the diagram construction. We should, in theory, use to solve these ambiguities the heuristic rules 2 and 3, but I didn't have time to implement also those two. Then let's see how they are implemented, again in the code, by considering always the previous example where we have B0 all non-positive. So here we see what happens, how to calculate exactly the coefficient flux when B0 is all non-positive, because here we have 0, -1, and 0, once again. Here we calculate the coefficient flux of the species NH for the NH3 reactant 0 to the product NH2. Here we will consider the number of atoms of species J. So in this case, we have hydrogen equal to 3, and we sum it with the B0 vector. And so we sum it with the -1, because the hydrogen here is -1. And then here we know that the sum of these two gives 2. So 2 hydrogen will be moved from NH3 to NH2. Instead, if we consider the product 2, so the water in the reaction, we will see that the coefficient flux will be calculated as a minus B0 vector, which is 1. So 1 hydrogen from NH3 will go to the water. So in this way, the element tracking is successful, and since we know exactly where the hydrogen is coming from and where it is going, and we can implement this rule into the code for B0 all non-positive. Same thing has been done also for B0 all non-negative, B1 all non-positive, and B1 all non-negative. So same type of code we will find also for the other options. Now we need to talk also about other approximation, because not only the ambiguities linked to the B0 and the B1 are not solved, but I had to do also other approximations. First of all, I need to do this type of approach only for reaction with 2 reactants and 2 products with the element. So if we have, for example, more than 2 reactants or products, the reaction at that point is again ignored, because I couldn't solve the ambiguity. Then the same species, when the same species appear among both reactant and both products, I made another approximation, which is the species will be deleted from the reaction that will be analyzed without it. So this here an example. So if in the reaction we have a third body, which is not really having a real reaction is not really having a change of molecular fragment, for example, the argon in this reaction, this element in this case, but in general can be a molecular, can be deleted from the reaction. And also for the second reaction that I have listed in the example, we delete here also the hydrogen and pretend that the reaction is simpler and it's easier to analyze. But this approximation can work only in special cases when it is really a third body that it's not actually involved in the reaction process, but sometimes this could not be the truth. So we need to also understand it to adjust this issue to take in account also the same species in both reactant and product. And this is done in this piece of code, where we first check if the species is both in the left-hand side and right-hand side of the reaction, and also if the stoichiometric ratio in both sides is the same, because once again we need to be consistent and ensure the conservation of the mass. And then we just remove the species from the equation and continue as before. Now, the element flux calculation also needs that the reaction rate is retrieved. The reaction rate, once again, is the velocity at which the reaction is proceeding. It can be calculated through this formula, and where we see Kf and Kb, which are the forward rate and the backward rate of the reaction. So the forward rate is calculated in this way. The backward rate uses the equilibrium constants, which is also calculated as in the slide. And now here we see that we need some information from the simulation. So we need the concentration of the species A, of the species B, of the species C, of the species D. So of each species involved in the reaction, we need to know exactly the concentration inside each of the cell. And then we also need to know the temperature. Then we need to know the constant, the forward rate and the backward rate. And the other quantities that you see are just the stoichiometric coefficient, gamma A, and so on, and other empirical parameters, while the G is the Gibbs energy, so it just depends on temperature. So here we see that, first of all, we need to obtain the thermophysical properties of the mixture. Then we need to obtain the chemical kinetics models. And then we need to calculate, in the end, once we have all the information, finally we can calculate the reaction rate. This needs to be done for every time step we want to use this post-process utility, because of course concentration and temperature will change if the problem is not stationary. So we need to calculate this and do this retrieval of the reaction rate for each time step. So inside the time loop. So let's see how this is done in the code. We first create an object called multi-component thermo. This will be constructed based on the mesh that we will need to give. And using this object, we can have access through thermo to the thermophysical properties of the mixture, such as the concentration, the temperature, the density, and other key information that are needed for the reaction rate. Now we need to also obtain the chemical kinetics model. And to do this, we construct another object, which is the basic chemistry model object. And this will be constructed instead by giving in input the thermo properties that we constructed in the previous step. So we need to give the thermodynamic to have also the chemistry. And then finally, we can calculate the reaction rate by using this function, the reaction rate function, that is a member function of the class model chemistry model. And this will be calculated for each of the reaction that are involved in the chemical mechanism. And so in this way, we define this field, the reaction rate field, which is multiplying our formula for I, which is used to multiply as a multiplying factor in the formula. Now, we can also decide where we need to apply this element flux utility. We can decide either to apply it on the whole domain by summing and averaging all the element fluxes all over the domain, but we can also decide to apply it in a small part of the domain by selecting it, and the user needs to give to the post-process utility this information, so where this needs to be applied. And this is done thanks to the other if loop, where we need to give indeed the cell zone. And this, once again, it will make an average within this part of the domain, which can be either, for example, the flame zone can be interesting, or the rich part where we have more fuel or less fuel. It can be interesting to do in several zones of the domain regarding the combustion processes. So once we use our post-process utility, so element flux, we will obtain a file which is called total flux, then the element of the name of the element we want to track with the dot extension, which will look like a sort of table where we have the reactant on the first column, the product on the second, the other reactant, the one that is also helping the formation of the product, in the third column, and then we have the total element flux. Total because for each line we will have one reactant and one product, but this is done by looking at all the reactions that are starting from the reactant J to the reactant K. But since more reaction can start from one reactant and give the same reactant, this is looped all over the reaction that are summing over the reaction that start from the same reactant and end to the same product. That's why in this table, in the third column, sometimes we can see more reactant. Even in the last line, we see we have 4 other reactant, which means that we are considering here more reactions. And also we can observe that the total element flux in some cases is very small, like here, in other is very bigger, and this will clearly be seen in the diagram, because the smaller element flux will have a very thin arrow, while the bigger element flux will have a very thick and visually clear arrow. So at this point, we need to understand how GraphViz works. So we imagine to start with a dot extension, with a file with dot extension, because this is what GraphViz need to have as an input, a dot file. This inside this file, we imagine to write just this small code. It will give a visual interpretation like this one. like three nodes that are connected by arrow, and where we clearly see how the flow, let's say, is proceeding toward, for example, C. Then how can we use it on our utility? We said that from the post-process utility, we have this file as output. Then we decide to convert this with Python to make it compatible with the graph width formats. So we create this sort of very complicated file, which now I will explain. We see here the nodes. As before, we see here also, once again, the nodes. So we go from the species C2H2 to the species C2H. So these ones are the nodes. Here we have the labels. So we have O and OH. These labels, as already mentioned before, will be the label of the arrow. And they can be more than 2, can be even 5 or 6, because we consider more reactions that are going from C2H2 to C2H. And then we have the arrow size, which we can clearly see that is going from 2 to 0.8. So it's changing a bit. And it's because in the diagram, we will see that the arrow thickness will change every time, because some transformation are more important and relevant than others. So in the end, we obtain this type of diagram, which can be sometimes very confusing. And so we can try to zoom out in a specific zone, and we see that we have nodes that are connected through arrows, which are labeled with the other reactant. And also the thickness changes. And in this diagram, I decided also to make it even more clear, the change of the relative importance between reactions, by also changing colors. So a lot of options are possible to make it more clear how the pathway is proceeding. At this point, we apply it on a tutorial case, which is the counter.
Margherita, sorry, how much time still you need, because we are a bit...
No, we are a bit, just 5 minutes.
Okay, try to make it shorter, because
yeah.
2 minutes we should start the next presentation.
Okay, I will be fast. So we have the counterflow flame tutorial, where we have methane and air meeting in the middle of the domain, igniting. We run this tutorial with block mesh foam run, which will go into the control dict and check the solver and start the multi-component fluid solver. Then we will run our application, element C, and which will generate the files we mentioned before. And then we will use the Python code and generate the image we saw previously to generate, thanks to graph width, the final diagram. We can also run this in a small zone of the domain, for example, where there is more fuel, and then we will see that the diagram will look very different. And yeah, so here there are lots of future method development I need to also do in the next steps. Don't know if I have time to go through it, but anyway, it's just trying to reduce the level of approximation I did so far, and use some new methods such as machine learning for automatic reaction mapping. And with this, my presentation is over. Thank you, everyone.